go through our last slides of perceiving objects and scenes. And I include here the scene that he includes at the beginning of this chapter of this area of Italy where there are these buildings, these objects within the scene, but then the scene itself helps us also to recognize the objects. One way we might think about scene perception is to make this analogy of the relationship between figure and ground. So that figure-ground segregation is to object-scene, that relationship. So the figure being the object and the ground being like the scene, where the object is typically seen as compact and acted upon, and the scene is more extended and acted within. One of the ways we learned about scene perception early on was from Mary Potter's 1976 study, where she examined this question of perceiving the gist of a scene. She gave people a target picture or a target description, and then she flashed 16 pictures, each for 250 milliseconds, which is a quarter of a second. So they truly saw this entire scene for a quarter of a second. And I am going to do this quick explanation of iconic memory and how she's using each next picture as the pattern mask. So if I show you a picture and then I show you a white screen and I show you the picture for 250 milliseconds, you see that picture actually for a little over a half a second. So there's this estimation of what's called iconic memory. Our iconic memory is this very short sensory store that is estimated to last about 350 milliseconds for vision. It lasts, they estimate, about 2 seconds for auditory information, which makes sense that auditory information would hang around a little bit longer since it is here and then gone, whereas visual information tends to be more stable, and so that iconic memory is really quite short. But she's not giving us a blank white screen afterwards, right? Each time you see a picture, the very next, so I see the flowers, and then I see the girl clapping, and then I see the elderly people surrounding a woman, right? So we have these scenes coming one after another, and each new scene is wiping out that iconic memory. People are truly seeing these pictures for about a quarter of a second. If she gives them a target picture to say, this is the picture you're looking for, people pick out the picture with 100% accuracy, or almost. Target description, so girl clapping being the target description, we're still up at 90% accuracy. So just showing that we are very quickly perceiving the gist of a scene. Faye and colleagues, they wanted to examine this a little bit more specifically to figure out what are we perceiving and under what kind of time course. So they used the 250 millisecond time, but they also used a 27 millisecond time, a 67 millisecond time, and a 500 millisecond time. So the 500 milliseconds being a half a second. So presented scenes for times ranging between those 27 milliseconds to 500 milliseconds. And what they found was at 27 milliseconds, basically people could see light and dark areas, and that's all they were identifying. By 67 milliseconds, so this is less than a tenth of a second, right, which would be 100 milliseconds, would be a tenth of a second, they're already identifying the larger objects in the scene, which suggests that this is partly, this gist of the scene is partly how we're helping us to identify objects. By 500 milliseconds, we're identifying the smaller objects in the scene. Again, by half a second, we are identifying the scene and the smaller objects within that scene. If we're asking the question now, how are we getting this scene and these objects so quickly? We're recognizing the small objects within a scene within a half a second. Well, Oliva and Taraba have done some work looking at scene perception, and one thing that they picked out were these global image features. So specific features of a scene that we are picking up holistically They're perceived very rapidly, and they are associated with specific types of scenes. So they're basically giving us this in to the scene, right? And so those are the degree of naturalness, the degree of openness, degree of roughness, degree of expansion, and the coloring in the scene. And I'm going to go through these with some examples from the book. If we look at these three scenes and we pick out each of these global image features, the degree of naturalness, we can see that in the left scene and the middle scene, there's a great deal of naturalness. And in the far right scene, there's very little, right? It's mostly buildings, a few little trees there. The degree of openness in the left scene, we can see it's very open, right? There's this open sky horizon. In the middle scene, it's very closed. We're seeing just these little pieces and parts, and the horizon's kind of blocked off. In the right scene, we actually have a degree of expansion there. What's being given by those parallel lines kind of coming together with that depth perception is this degree of expansion. And so it's somewhere in the middle as far as openness. It's somewhat open, but it's not truly open like the scene on the left. The degree of roughness, it is the scene in the middle that has the most roughness. There are more little tiny pieces, we could call it high spatial frequency, as it's rough. The scene on the left has some roughness towards the bottom and to the right of the scene. The scene on the right has roughness in places, but not throughout the scene, really, the way the one in the middle has. For the degree of expansion, I've already kind of gone through that a little bit by saying that one on the right has that degree of expansion. Those parallel lines coming together, like that gives us this sense of depth in the scene. It gives us this sense of expansion. The other two scenes have much less. And then the coloring also tells us about the scene. So blues and beiges, the kind of sand and sea, those kinds of colors tell us we're at the beach. The greens and browns of the forest can tell us we're in the forest. Buildings, oftentimes buildings are kind of grayscale, cement, or brick, but even the coloring of the building can tell us quite a bit, like whether we're looking at adobe houses or Rainbow Row in Charleston. Those colors tell us about the scene. And again, these global image features are rapidly and holistically just pulled out of a scene, helping us to get into that scene and helping us to see the objects more quickly. These physical and semantic regularities, these things that we are used to seeing within specific scenes, they help us to comprehend scenes and then the objects within the scenes. Go through some physical regularities first. You might not be surprised to find out that there are more vertical and horizontal lines than there are oblique lines. This oblique effect that we saw at the very beginning of the semester, that we tend to see vertical and horizontal lines better and longer at lower contrasts when they're more narrow and all of that, and we have more neurons responding to vertical and horizontal lines, it is because there are more vertical and horizontal lines in our world. Our buildings tend to be built that way. Tree trunks, things in nature also tend to be vertical and horizontal. There are oblique lines, but there are fewer of them. Another regularity is this, comes back to those Gestalt principles. This one is uniform connectedness. So if we have something that is the same texture, contour, and color, we're going to assume that that continues even if it's occluded, right? So those men's pants, they're not stopping and starting every time there's a bar in between them, right? We know that that is continuing behind there. That's a regularity from our environment. Regularity in our environment is the light from above heuristic, that we assume light is coming from above. When we're outside, light comes from the sun, it's coming from above. Most of our lighting is above us. If you've ever been in one of those places where there's lighting at your feet, you can kind of look up and notice some of the easy misinterpretations that you can give yourself, which I think is kind of fun. I do like perceptual games. So if I ask people what this is, and I usually do this in class of asking you, what does this look like? and people say some kind of crater, right, with a little mound in the middle. But that interpretation is because of the shadowing, right, and this assumption that light is coming from above. And I can show that by flipping it upside down. These are some of my favorite games in class. I don't know why. It just makes me happy to pull out, and in videos I have to do a little bit differently. Now we have a mound, right, with a little tiny crater inside it, because again, I've turned that upside down, and we're still assuming that the light's coming from above. So we're interpreting those shadows. Those shadows appear different, right? They make the picture be different for us. A semantic regularity, so getting used to this word semantic, which means basically meaning, the meaningfulness, right? And we also have regularities of what we expect to see of particular objects that perform particular functions, that they're going to be in different kinds of scenes. And so Andrew Hollingworth did this study where some of the times you would see a scene like this and the barbells would be there, and then later they would show you the scene without the barbells and ask you where they were. And so you can see the little smaller circle that says present. If the barbells were present, people put them basically within that smaller circle. Then they would show, so sometimes they would show the scene without barbells, and then they would show the scene later and ask where would the barbells be. Well, when the barbells are absent, they're within the larger circle. So we're in a gym, we expect to see barbells, and this is actually where we expect to see them, right? Somewhere around that mat where I would be working, doing free weights. And I did this with all kinds of scenes, and it's a pretty neat result showing we have particular objects that perform specific functions that we're expecting to see in specific scenes, and actually we expect to see them in specific places. So nice example of top-down influence. One of my favorite old studies, I don't know why, I don't know why it's one of my favorites, but it's Stephen Palmer's 1975 study where he would show a scene like this one, like this kitchen scene, and then he would show, if you can see the pictures on the right, the top one is a loaf of bread, the middle one is a mailbox that shares a lot of characteristics, or the basic picture is similar to the loaf of bread, and then there's a drum, which is dissimilar, does not look like the loaf of bread. And then they showed these, so they showed the scene, and then they would show the picture, and it was for some varying amount of time, something from 25 milliseconds up to 150 milliseconds or something of that nature, at those really short intervals where they were sometimes wrong. When we get into longer intervals, they were pretty good. They would be able to recognize the bread 80% of the time. When just asked, what is this picture? The mailbox coming up after the kitchen scene, they were at 40%. The drum coming up after the kitchen scene, they were at 40%. And this was all nicely counterbalanced, so the mailbox would be after for other people, for different participants, after a street scene where the mailbox makes sense. And so nicely counterbalanced, really nice study showing that I have this scene and it's helping me to recognize the object. Another study that shows a great example of our use of semantic regularity. What we expect to see in different contexts influences our interpretation of something that's very ambiguous as well. And this is another Oliva and Torralba study that was done in 2007. So this is the blob. I actually like this study because it's called multiple personalities of a blob. So they are photoshopping this blob into these different scenes. The blob itself is exactly the same. And when I walk through this in class with students, we say, what's in B? I get some different answers, but sometimes people say a cup, or I don't know. So that one's a little bit ambiguous. In C, people say clearly it looks like a shoe, like a person's shoe. And in D, I usually get a car and a person, even though to me they kind of look upside down, like shadows in the water or something, but whatever. That's what people say. But you can see the point of this is the same blob, right? And it depends on the context. If we put it in this blurry context where we kind of have an idea of the scene, it tells us how to interpret that blob. So again, really nice evidence that we have these semantic regularities, things that we expect to see in particular scenes. So as we come back, I'm going to come back to this, to object recognition and how we're doing this, and to how scenes really help us. We had some theoretical approaches to object recognition, and I asked you to really think about what are some of the issues where we're not answering our questions. Well, I feel like Bayesian inference answers some of those questions for us. And Bayesian inference comes from Hermann von Helmholtz, whose name we will see several times throughout this class. He came up with this theory of unconscious inference, that some of our perceptions are the result of unconscious assumptions that we make about our environment. So if we look at what's happening in A, and I ask you, what do you see there? Almost everybody says. In fact, I've never had anybody not say. There's a purple rectangle or blue rectangle in front of a red rectangle, right? They're always labeling those as rectangles. If I told you instead that this is some upside down L that's resting on top of a purple rectangle, you would say, we've done this, right? Okay, I guess I can interpret it that way if I work kind of hard. But what's more common, right? We've made this unconscious inference that it's a purple rectangle in front of an orange rectangle. And we might think of simplicity or some of those Gestalt principles that helped us to get to that. But rectangles are also more common in our environment. If we take this into looking at particular contexts, we can use this kind of likelihood principle given this context, or given the available information, and based on my prior experience, where I'm talking about really the probabilities of how often have I seen this specific, right, object. Bayesian inference has a mathematical calculation that I'm not going to go into the mathematics of it, that we're making these inferences based on the prior and the likelihood, where the prior is the prior probability. How often have I come across this particular object? And the likelihood is, what is the likelihood of this object given the available evidence or the available context? So, and they really, this is getting very specific about what that likelihood principle, right? So in Hermann von Helmholtz, this is a likelihood principle, and now we're specifying, and actually specifying mathematically, that likelihood principle. I'm going to walk us through this example that he gives in the book, which isn't necessarily about visual perception, but just this interpretation. So Mary's friend Charles has a cough, and we might ask, what is she going to assume? Like, why he has this cough? She might assume why he has this cough. We look at the prior, so belief about the frequency of things in the world. If we look at the frequency of colds, those are really quite frequent. The frequency of lung disease is much less frequent. The frequency of heartburn is also quite frequent. So these are just some examples of what might be causing, right, his cough. If we look at the likelihood, so the chances of this particular kind of disease causing a cough, the likelihood that a cold can cause a cough, that's very high. The likelihood that lung disease would cause a cough, that's very high. The likelihood that heartburn would cause a cough is lower. And so we basically multiply these out in such a way that because that cold was both high in prior, high in frequency, as well as high in likelihood, that's the highest in the conclusion of this is probably the hypothesis that Mary's going to make, right? That Charles's cough is probably due to a cold. It's less likely to be due to lung disease because the prior is low on that. It's unlikely to be due to heartburn because even though we've seen that it's frequent, it's heartburn is not likely to cause specifically a cough, like the likelihood given the context, right? So this is a funny example, funny, strange in a way, but I still kind of I like it. One of the things I usually note with this prior that I think is really important because of what I ended up studying was language and these syntactic structures, the structures that follow a specific verb, it looks like it is as if we are calculating the likelihood based on experience, because the percentage of time that verb is followed by a particular structure influences my interpretation. And so this appears to be really the way we are implicitly learning about our world, is that we are um, basically collecting these probabilities. So this prior is a very real thing, where early experience and really recent experience are both very powerful. Early experience before the hippocampus um, is truly formed while it's still forming is very powerful. So before we're 4 years old, but then also our recent experience, like we did that perceptual set in how we are interpreting some ambiguous figure, that is also very powerful. But another thing that the textbook brings up is the power of this prediction error. So part of Bayesian inference is that we have a prediction error. If my high level or my top-down processing, my high-level predictions are coming down, and my information from the receptors is coming up, that is meeting somewhere, right, where I'm experiencing my world. And if there's no difference, then there's no prediction error, but I'm just quietly, nicely collecting these probabilities. But if what happens instead is my top-down predictions, my high-level predictions, or my expectations, those are coming down from the top-down kind of manner, but we have unexpected information from the receptors. So you come into the classroom one day and there's an elephant or whatever, and they have this darker arrow here. That's coming up and it's really clashing, right? There's this difference. And so we're sending back to the brain this prediction error of what now that we can expect potentially in this particular context, or what kind of objects we might expect in our world, in our environments. So an updating. I am skipping to the end of the chapter, and I'm skipping a little bit of really neat research on neural mind reading, that we can make predictions now from people's brain activity about what they are perceiving. But I'm going to go into this bit of neuronal specialization. So we talked about these modularity of processing, that we have these modules that are responding to specific things, like we have the fusiform face area that responds to faces, as an example. But this neuronal specialization, we know that part of it is that there's an evolutionary component, that we're born with a basic architecture to the brain. That overall layout is going to have some preset basis. I usually do the example of the letterbox. So the letterbox, if I'm not dyslexic or left-handed, I suppose things can be kind of different, but when we are reading, we have the visual information goes back to the occipital lobes, and it is quickly kind of shunted over to the left side, and there is this little tiny region that, if that region is damaged, then we're going to lose our ability to read. And this letterbox that exists somewhere right around where the occipital and temporal lobes come together, that region is in the same place regardless of whether I'm reading a phonological language, whether I grow up reading a conceptual language like Chinese, whether I'm reading Cyrillic, whether I'm reading up to down, or left to right, or right to left, regardless of how I'm speaking or what I'm speaking, or what those characters represent, that letterbox is in the same place, right? So there's this really kind of architecture of the brain, but we also see that experience shapes the pieces and parts, right? That those details are shaped by experience. I'm a pretty big proponent of remembering that we have this experiential dependent plasticity, that our brain will change depending on our experience, and thus if we want our brains to be good at the functions or the tasks that we want our brains to be good at, then we need to practice those tasks, because our experience is going to mean building those neural networks. So one of my favorite studies, because you might be able to tell here and there, I like to talk gibberish. I like things that are made up, and I like when people play with language. So in this study by Isabelle Gauthier and her colleagues, they had people memorize these Greebles. And so there were a number of them, not just four, but these are four examples. You can see they kind of almost have little bird faces, but people were naming. So they gave each of these a name, and people were trained up on learning the Greeble names. I might get my exact numbers wrong, but it was something like 7 hours for 4 days or 4 hours for 7 days. They had a lot of practice until they got to know the names of these Greebles. And what we can see in the figures on the right is we're looking at activity in the fusiform face area, that specific region that is helping us to identify faces. And before the training, they were shown faces and they were shown these Greebles in the fMRI, and we can see activation to faces, but not to Greebles. Then after training, that area really changed. Now it's responding to faces, but after I've learned to name these Greebles, I've become a Greeble expert. That region of the brain is also responding to Greebles. So it looks like, or what they suggested from this study was that we might call this fusiform face area uh, an expertise area. As I mentioned before, we prefer faces, we're familiar with faces, we are experts basically in learning people's faces. Even if we're not that good at it, we're experts at it. We recognize so many faces. But apparently, if I'm an expert at knowing cars or birds or butterflies, this region of the brain is helping me to identify something that I'm giving all those names to and becoming an expert in. So nice, excellent example of experience-dependent plasticity. And that is going to be where I end on the objects and scenes. And we're going to move on into talking about hearing and the auditory system.